All right, we're live. We've been going through spin orbit coupling, as you all are aware by now. So we get all the matrix elements and have this spin orbit coupling Hamiltonian, and this is what they look like in our original basis, in terms of the x, y, and z. And so before we did all this work, this is the AA block, just the A atom coupling to itself. Down the diagonal, if you just look at the diagonal elements, that's what we had before, this epsilon s. Well, I guess I wrote it here with an S star, which we haven't talked about. So you'll see this, and I think I'm going to do this in the last homework assignment, have you actually calculate the band structure of, I haven't decided, probably silicon. And to get that X value right, you need this extra S star state. It's an excited, what it represents is an excited S state. So, we've just been using the sp3 orbitals of the valence shell. But if you want to be more accurate, you can start using orbitals of the empty shells up above. And people do that all the time. And you have to do that in silicon to get the X value right. If you don't have this, if you just use your sp3 basis that we've been using, what happens is that X value is way too high. And so you know how levels tend to, when they couple, they push apart. So out at the X, if you have this extra S orbital up here that's above everything, and it couples to the P, then it pushes that down and gets it about the right energy where it should be. So this represents the S star. You'll see this in quantum chemistry codes. They always represented as like a star. So it's an unoccupied from the next shell up is what it represents. And I've kind of left that out because it's just one less thing to have to talk about. But if we're going to really, calculate the band structure of silicon, then we're going to have to include this. So you might as well know ahead of time what this thing is. At any rate, back to spin orbit coupling, what's down the diagonal, these epsilon p's, I'm afraid to write, are what we had before, and then all these other matrix elements came out of the spin orbit coupling. And it looks kind of messy in this S XYZ basis. Doesn't look very pretty. But now if you go to our new basis, that Jm, that total angular momentum basis, you go to that new basis, then your Hamiltonian looks like this. This is our Jm basis, the total angular momentum basis. I've written it for both. This is the whole thing, both the A and the B atoms. So these are the 4 blocks from the 3-half states. And notice the way I've written this, I have the A atom and then the B atom, the A atom, the B atom. And I have the same, if you look closely, the same state on each one of them. And as we talked about before, the matrix elements that couple the A atom to the B atom only couple the states with the same Jm quantum numbers, those same total angular momentum quantum numbers. And so, if we just looked at the AA block or the BB block, it's completely diagonal in this basis, and the 3-half states get raised up by a factor of delta over 3, and the J equal 1/2 states, these two guys down here, get lowered by this negative 2 delta over 3. And so we've broken this this 6-fold degeneracy into a 4-fold, the 4 red blocks here, which are from the 4 3/2 states, and the a 2-fold degeneracy due to the J equal 1/2 states. So that's as far as we got last time, and this is it's only this simple at k equals 0. So this is only true for k, this form for k equals 0, right, at gamma. This is the only time it gets so simple. Otherwise, you get a lot more matrix elements. So this is what we spent, a long time getting to this point to understand what the spin orbit coupling does. Any questions? So now I'll just draw some pretty pictures. The spin orbit coupling it splits this six-fold degeneracy that we initially had into a four-fold and a two-fold. And this four it will become your light hole and heavy hole bands, and this two will be your split off band. So this was down, this is the one that got lowered by -2 delta over 3, and these are the two that got raised by delta over 3. So we started off, everything was at epsilon sub p, and then the light hole and heavy hole get raised up by delta over 3, and that split off band gets lowered by -2 delta over 3. And so the total splitting is delta. And if we then look sort of pictorially at what happened before we turned on spin-orbit coupling, we just had 3 bands that were completely degenerate at gamma. They're all have the same energy right at the gamma point. So if I include spin, this is our six-fold degeneracy at gamma. And now when I turn on the spin-orbit coupling, I raise up 2 of the bands by delta. One will be the heavy hole, one will be the light hole, and then I lower, so they're raised up by delta, and then this band down here is lowered by 2 delta, and this is your split off band. This guy is lowered down by 2 delta, 2/3 delta, and it's your split off band. These guys are raised up by delta over 3. And you got your heavy hole and your light hole bands. The heavy hole band, we haven't proved this or derived it, but it is, in fact, the 3/2 plus comes from the 3/2 plus or minus 3/2 states. And the light hole has to come from the other two, because they all are j equal 3/2, so it's 3/2 plus or minus 1/2. And then the split off comes from the j equals 1/2.
Is it degenerate in reality?
I'm sorry, what's that?
Is it degenerate in reality?
Which ones?
So upper ones.
Yeah, right at k equals 0.
What about the Pauli exclusion principle?
Well, I mean, the Pauli exclusion principle just says that you can only put, 1 electron in a state, but if I have, it doesn't say that it doesn't say anything about how many states I can have at the same energy, right? That's just degeneracy. Just like in a particle in a box, the first level is not, like a two-dimensional box. The first level is non-degenerate, and then, as you go up, you start having, multiple ways you can make a state, and your energy levels start to be degenerate. It's like you can have kx, one direction kx can be 2 pi over lambda, the other can be pi over lambda, and then you can switch it, and the energy is identical. The 2 different states.
All the states share 1 electron. Yes?
What's that?
All the degenerate states share 1 electron. Yes?
No. Every state can have 1 electron.
You have more than
Every
one
state can have 1 electron. And remember, they're orthonormal too. Those states are orthonormal.
We have 4 states.
You can have 4 electrons. Yeah.
4 electrons with the same energy.
Yeah. One sort of stupid example is if my states are just spatially 1,000,000 miles apart and they're at the same energy. I can have 2 electrons in them. That's like 2 atoms far apart. Same energy. 2 electrons.
But if we have correlation, they begin to split.
What's that?
But if we have any correlation, they begin to split.
Well, for splitting, you need a non-zero matrix element between them. So you'd have to have something that gives you a non-zero matrix element between the states to split them. And if due to symmetry reasons or whatever, you may not have that. So these guys, which are in this model completely degenerate, you can basically think of them as like 2 orbitals and 2 spins per orbital. That's how we start. We start with 2 orbitals and 2 spins each. So specifically at k equals 0, these states, the heavy hole state 1 over root 2, 3 halves, plus minus 3 halves, minus, and this is on the A atom, minus, and this would be for silicon where both atoms are identical, 3 halves. This is on the B atom. And the same form then holds for all of them, for the light hole and the split off. All right. And, these are our valence. These are our valence bonding states. And so usually you think, it's the same thing that happened when we were just dealing with straight with the p orbitals. Usually you think of a bonding state as being like the sum of the two, being a symmetric combination. But because these things are antisymmetric to begin with, because they're p orbitals, it's the antisymmetric combination of antisymmetric states, which gives you this symmetric state under inversion. So these guys are symmetric under inversion, and they are the bonding states. They're also called U and Cardona, one of the books listed in the syllabus. They use a lot of group theory notation, and if you ever start looking at EK plots in the literature, you'll quickly run into this kind of stuff. So these are referred to as the gamma 4V states in U and Cardona. For direct gap material, the conduction band just stays, that is unaffected by all of this. And we just keep our old basis of just S up and S down. So nothing changed there. And these are the referred to as the gamma 1C states. Again, if you look in U and Cardona, which at this point you may start to understand some of what's in that book. Well, I guess that wraps this up. I wanted to say something about the homework, and I know I'll forget if I don't say it now. So the homework is posted, and we'll discuss it Friday, but just in case anyone wants to look at it ahead of time, long-winded, a lot of writing before you get to the questions. So I basically just included the entire solution of the last homework up front and just started adding on from there. So this is basically just a solution. So you have all the equations in front of you, and so I can refer to them also in the next homework. This is just basically solutions from the one you just turned in and all the diagrams. Okay, so finally, the new homework starts here. It's this linearization of the Dirac equation, or of this, what you just derived. And so if you go back and look at the Hamiltonian, the final, that 2x2 Hamiltonian, it's pretty simple. This is it. Equation 18, that's what you did. And you know exactly the form of V. You can write it like this, or you can even go back and write it as a sum of exponentials. And so in the next homework, what you're going to do is what they say is linearize it around these high symmetry points. So K is one of your K points, and then you just do a first order Taylor series expansion of V around that K point. So this constant term drops out because you've already shown that V at the K points is 0. Right? So that's gone. So basically you're just looking at this. And so you go ahead and you take the gradient, and that's why I kind of like to go back to the exponential form, because taking the gradient of exponentials is really easy. And you end up with something that looks like this. And then at this point I leave it up to you to evaluate that thing. And this becomes your new, what you would call your linearized V. Okay, this is going to be linear in V, because this is independent of K. This is just evaluated at K1, and to be specific, K1 was this K point right here. Here's K1. I chose a very nice, easy K point to evaluate that at, okay? So you evaluate it at K1. So there's no K dependence to all this. It's just some number. And your K dependence is out here. Well, that's clearly linear, okay? And then we just call this, we quit writing K minus K. We just sort of say, okay, we understand that this K is centered around that K point. Just write that as K. Like for a K that's centered around the K point of interest. And so now you get a coupling that's going to be linear in K. And so you go ahead and you evaluate that, and then you just write out your new 2x2 Hamiltonian with these new linearized V's. Okay, so now you're going to have a Hamiltonian that the diagonal elements are 0 because we're doing graphene. We just set the diagonal elements of the carbon to 0, and you've got something that's proportional to K on the off diagonal. And so you can immediately picture that probably by now in your head and realize immediately that E, the energy, is going to be proportional to K. Because E squared will be proportional to K squared, take the square root. And so you're going to have a linear dispersion relationship, this famous linear dispersion of graphene. And so once you figure that out, so determine the eigenvalues, that means just, you're going to get like E is equal to plus or minus something times K. Because you'll have one for E above 0, one for, it's like your conduction and valence band, even though there's no band gap. Right? It's a 2x2 matrix, you're going to get two eigenenergies. It'll be of the form E equals plus or minus something times K. And then I say, go ahead, and this goes back to what we were talking about last time. Put in here, and I'm telling you to use T of 3 eV this time. Put in the specific value of T, and then calculate the velocity of your graphene in centimeters per second. And this is where people have a heck of a time. I mean, up to now it's been all sort of formal, but to go from 3 eV into centimeters per second with some H bars, people have. It's usually the units that kill everyone. I mean, it's not, the formulas are simple. It's just the unit conversion is difficult for people. Because this is not an MKS unit, all right? Just be aware. EV is not MKS. So you'll compute this, and it should come out to, I guess, something on the order close to, what did we say last time? 1/3 the speed, 1/300th the speed of light.
100,000.
Is it's something close to 10 to the 8 centimeters per second. Something close to 10 to the 8 centimeters per second. Maybe a little under, like 9 times 10 to the 7th or something like that. Right? This is 1 over h bar dE dk, and so let's see, if you use h bar in eV seconds and you put your A, this lattice constant, in centimeters, it probably should all work out. Now you have to, just be careful. You'll have to just deal with the units. Keep track of your units. And then I sort of, in the next problem, give you the answer. So this is, if you go through, if you take this derivative, you're going to get that the velocity is equal to this. Calculating, T is 3 eV, A is the lattice constant. You divide through by h bar to get V. And but you can check everything you've done, because this is what the velocity should look like. Be careful, there's two A's floating around. This A is the lattice constant. And I said, and the only number you've been given so far is ACC up here, and I think it's like hidden away in a figure caption. So ACC is given right here, 1.42 angstroms. So this is ACC is the carbon-carbon bond length, right? And A, the lattice constant, is square root of 3 ACC. There's two different A's to keep track of. The lattice constant and the carbon-carbon bond length. So also, when up above, when I tell you to write your Hamiltonian in this something that's linear in K, well, you can go backwards. This is what it should look like. These sigmas are your Pauli matrices. You can expand them out and add these two terms together, and this is what you should see. And this is usually the way you see it in the literature, actually, this linearized form of the Hamiltonian. written in terms of the Pauli matrices. And often you'll see something that looks like this. Okay? For any 2 by 2 matrix, you can write it as a linear combination of the Pauli matrices plus the identity matrix. Those are 4 independent 2 by 2 matrices. There's 4 elements, so you can make any 2 by 2 matrix out of a linear combination of the 3 Pauli matrices plus the identity matrix. And so the physicists like to write it as some linear combination of the Pauli matrices. It's a very generic thing. And in fact, once you do that, you can immediately write down the eigenenergies and eigenvectors. Solve it once and for all. Anyway, so, and I sort of set you on the road to doing that down here when I say factor out the magnitude of k from, say, your Hamiltonian here. Factor out the magnitude of k, so you'll have a k out front, h bar vk, and then you have like a kx over k, a ky over k. And these values are just the cosine of the angle and the sine of the angle with respect to the kx axis. That's what those are. Just the cosine and sine of the, in a 2D kx, ky plane, that's just the cosine and sine of the angle with respect to the kx axis. It's the angle of your k vector with respect to the x-axis is what that is. And so you can write your Hamiltonian in terms of, because sigma y has an I in there, you're going to get terms that look like this, which you can combine into these e to the plus or minus I theta. And you can write your Hamiltonian in terms, these off-diagonal terms can be written in terms of this e plus or minus I theta. And once you write it like that, then it's very easy to calculate the eigenvectors. And so that's what I have you do somewhere. Show that. And finally, once you calculate these things, the final thing. What else is there? The next to final thing is show that if you're in a single Dirac cone, like at one of the k points, that if a state moving in one direction is orthonormal to the state moving in the reverse direction. And so if you take the inner product of these two states, you get 0. And that serves to suppress backscattering and is good for, say, mobility. It reduces, it's harder for an electron if it's moving this direction to get flipped back the other way. And finally, the last problem is, given this linear EK relationship, calculate the density of states. So that's what we're doing. It's due 2 Fridays from now, so we can discuss it next Friday. But if anyone wanted to look at it ahead of time, I just wanted to give you a heads up. The other thing I'm going to do, I think, since it's due 2 weeks from now, and we're starting to get short on time. So if this is due, 2 Fridays from now, that's like the end of week 9. So I'll probably put the last homework up there, whenever I finish it, and have it be due anytime during finals week, I guess. But I'll get it up early, so if people don't want to, be around finals week, get it done early. Okay, so that's to deal with the homework. And finally, I just give you some historical, this very famous paper by Kane and Melle, which, a Fizerev letter, they just write the Hamiltonian down like this. And I go through the derivation and show that it comes out to exactly what you've just derived in 208. So we are done with spin orbit coupling. Hurrah. And now we can start something brand new. So what we're going to start is K dot P theory, sort of a whole different approach to band structure. This is used extensively in optoelectronics. So for example, have you all heard of a quantum cascade laser? You've heard of a quantum cascade. You did your thesis on it, didn't you? Yeah, okay. Quantum cascade laser. A quantum cascade laser is probably the most sophisticated heterostructure that's ever been built and actually made it into sort of the commercial realm. It's made out of all direct gap 3-5 materials. They have to get very, very good band alignments. They use multiple quantum wells, barriers, and to get all the band alignments correct, they use quaternaries, which means alloys consisting of 4 different materials like indium, aluminum, gallium phosphide, and stuff like that to get their all the band gaps and energy alignments correct. And all that design of those devices was done using K.P methods. And because, well, it's an optoelectronic device, and everything of importance happens right around gamma, at the gamma valley. And so K.P theory is really good for direct gap materials if all you care about is stuff near the gamma valley. This is great for, the people in optoelectronics, they deal exclusively with direct gap materials, such as your gallium arsenide, indium arsenide, etc. And so you're only interested in states near gamma. Unlike what we just did, which is good for the whole Brillouin zone, can capture the entire Brillouin zone. This is a perturbation theory, and you start with the known band structure at the band edges at gamma, which we've just calculated in gory detail. And then you use, so this is all at k equals 0, and you assume you know the states at k equals 0, which we do because we just calculated them. And then you use perturbation theory to describe the bands as k moves away from 0. So as k moves away from 0, you're sort of dealing with that through something like a perturbation theory. And it's really what you call an envelope. You're really solving for the envelope of the wave function. So, we solved what we were just calculating in our localized orbital. We're actually calculating the form of those underlying block states that get repeated every unit cell. Here, you start off with the block states at gamma, and then everything is written as a linear combination of those block states as you move away from k. So your basis is your 8 block states. So at k equals 0, that's sort of if you think of sp3 on each A and a B atom, we had 8 states to begin with, and that's your initial starting point, those 8 states that we just calculated. And then to understand, as k moves away from 0, you then write, the new eigenstates as a linear combination of these 8 eigenstates at k equal to 0. And I guess there's really nothing wrong with that. But, people used to get into heated arguments about things like you really can't take into account, in this theory, interfaces really well, because, say, an MBE grower can grow a quantum well or grow a crystal that, like gallium arsenide, for example. So the surface, if you're growing a quantum well, could terminate on the arsenic atom, or it could terminate on the gallium layer, because they grow in layers, gallium, arsenic, gallium, arsenic. And if you're doing an atomistic model, like we did in our localized orbital, then that's all automatically taken into account. But in this, you really don't have any information about the individual atomic layers, because you're using as your basis state these bulk states at the gamma point, which are just a linear combination of the A and the B atom. So you can't handle things like what I just talked about, whether your quantum well ends on a gallium or an arsenic atom. So it's not really as good with handling interfaces, or when you go to just large-scale three-dimensional calculations, if you're using an atomistic model like what we've been doing, then you can imagine interfaces which just are a mix. Say if you're going from gallium arsenide to indium arsenide, you could have an interface, a layer which is a mix of gallium and indium atoms. Right? And that's in fact what happens when you grow it, depending on how you grow it. And so you can explicitly put in some random distribution of indium and indium and gallium atoms, and just explicitly solve it in your localized orbital in an atomistic model. And here you really can't. But it's really worked well for people doing designing lasers and these quantum cascade lasers. It's been very powerful, and also it allows you to work with smaller matrices. So it's numerically, if you can get away with it, it's a cheaper way to go, which we'll see as we get into this. So it's really sort of an envelope function. What you're calculating is the envelope, how much each of these states is weighted, rather than getting into the individual atomic orbitals. One of the key parameters, just like in our tight binding theory, we actually had a lot of parameters, like VXX, VSP, which at the end of the day are usually just chosen empirically to give you, the right band gaps and effective masses, which are known experimentally. Here, the important sort of parameter, one of the key parameters, is the interband momentum matrix element. The interband moment, and this is something that's just empirically determined, but it's sort of a core, it's sort of a key thing. I mean, K dot P. This P is what we're talking about in the K dot P. This P is this essential central parameter to this theory. And once you have this P, another reason that it's really nice for optoelectronic work is that this is the same momentum matrix element you need to calculate all optical transitions. To calculate optical transitions, you need the matrix element of the momentum operator. And so you immediately have it sort of built into the heart of this theory. Whereas in the localized orbital tight binding theory, it's there's been many papers written about how to appropriately calculate the momentum matrix element in your tight binding theory. I mean, if you really start to think about it, we kind of never really talked about the momentum matrix element, right? And so in tight binding, in our localized orbital tight binding theory, we just wrote down a Hamiltonian of p squared over 2m plus, some sum of all the atomic potentials, for each atom. But now, and we took the matrix element of that, we got parameters, and then we sort of parameterized it. But now if I say, okay, given, some S on the A atom, I don't know, px on the B atom, what is the momentum matrix element? Nobody really knows. There's been lots of papers written on the appropriate way to do this. But you'll see in this K dot P theory, it just it's obvious. Okay, and again, this is, if you want to do optical transitions, this is what you're looking for. So we are going to be considering a direct gap semiconductor, which means, well, for us, you can have, as we've seen, a direct gap with band edges at, say, the X point, like in our polyacetylene, but we're going to assume that our band edges are at K equals 0, direct gap material like gallium arsenide, and you assume that the eigenvalues and eigenfunctions, i.e. the block functions, are known at K equals 0, and they actually form the basis in which you work. So these eigenfunctions are your block functions. And so these, we just calculated with and without spin-orbit coupling. Right? So without spin-orbit coupling, which is actually the way they do this in K dot P theory, you're going to have, your basis will be the p orbitals and the s orbitals at K equals 0. And then they'll put in spin-orbit coupling explicitly. So you assume you know these, which we do now. We've gotten pretty good with this stuff. And then, well, now let's go and write down our Schrodinger's equation and then start manipulating it. We have p squared over 2m plus some potential acting on psi. I'll explain this index. Where n is your band index, right? We're using these known band states that we just calculated as our basis, and that's equal to the energy of that band, which say is your valence band or conduction band, times the wave function again. Okay, that's just Schrodinger's equation. And so the known solution has the block form, and the block form of any block function is periodic, some periodic part, which repeats every unit cell, and then the plane wave multiplying it. So psi n is going to equal the periodic part of it, un of r, times the plane wave. But recall, this is at k equals 0, right? So at k equals 0, we don't need to worry about that. And this u is periodic, and so un of r is just our usual periodic part of the wave function, where r is your usual lattice vector. And these things form a complete orthonormal basis as usual. So u n r e to the I k dot r, orthonormal basis. And this is the basis we're going to use in k dot b third. Okay? So what we do is we put one of these, we just wrote down Schrodinger's equation, and now we just replace psi with this guy right here. So wherever we saw psi in our Schrodinger's equation, we're going to put in this, because we know this is a form of psi. Okay? We'll go ahead and do that. We have p squared over 2m plus v. And this v just represents the periodic potential of your entire crystal. Acting on u can be in general a function of k also. And that's just equal to E times the same thing again. And E will also have the indices for the band index. It's a function of k times u again. Okay, I just replaced everywhere I had psi with this special form of psi of a block function. And then what we do is we evaluate that p squared term, which, the p squared term is minus h bar squared over 2m grad squared, hitting everything to the right. Right? That's what that p squared term is. And so that acts on everything to the right, which is our, so this has, the u has some spatial dependence, and the e to the I k dot r has space. So it's going to hit both of those things, right? You got to use the product rule, and you got to do it twice because it's grad squared. And so it takes a few lines, first to do, and you can think of it as ddx and just do it in 1D if you like. But so you crank that out, and I used to write all this down. So I'll say see page 6-3 of the PDF notes if you want to see the details of working that through, the tedious details. So right, you just apply it twice to that u e to the I k dot r term. And what you finally get is, what do we finally get? We finally get that p squared minus h bar squared over 2m grad squared u e to the I k dot r is equal to p squared over 2m acting only on u. So when I close the parentheses, it does not act on the e to the I k dot r now. Plus 2 times h bar k over 2m dotted into p, which is again only acting on the u term with an e to the I k dot r sitting out here, and plus the last term h bar squared k squared over 2m u e to the I k dot r. So that's what I get from applying grad squared twice to this product of u times e to the I k dot r. And I still have, what have I got? I'm still going to have a v times u times e to the I k dot r. So I'll also, just going along for the ride, I continue to have my v u e to the I k dot r. And all that is equal to, on the right-hand side, this, which doesn't change, right? And so if you notice, every term has this phase factor on both the left-hand side and the right-hand side, right? It's no longer being acted on. Every term now has this phase factor in it, which is now outside of the derivatives on both the left and right-hand side. And so you can cancel that phase factor out from everything. And now you just have an equation for the u, the periodic part of the block function. Because, you know, the e to the I k dot r is kind of a trivial term. And if you look, here we have a k dot p, hence the name of the theory. We've picked up something new that wasn't in Schrodinger's equation before. Before we had this term, we still have a p squared over 2m acting on u. We get this extra, this is just a number now that depends on k, right? It's just this free particle energy, h bar squared k squared over 2m, parabolic type energy, multiplying u. We've still got the potential multiplying u. So all these look like terms that you could end up with in Schrodinger's equation. But what's completely new, we haven't seen before, is this k dot p term. Hence the name of the theory. And so if we finally write all this out, the equation for u that we have is p squared over 2m plus h bar k dot p over m plus h bar squared k squared over 2m plus your crystal potential, this periodic potential due to the whole crystal, acting on u is equal to the energy times u. And so this is our starting point for k dot p theory. And everything, if you just saw this, okay, you've got this funny, this is a little strange, but it looks just like some, parabolic kinetic energy term proportional to k squared. All right, and this, you've always been dealing with this term right from the beginning. That always shows up in the Schrodinger equation. Your potential, well, that's always there, but this is this new thing, this k dot p term. And now let's talk about perturbation theory and what you can get out of this, some of the relationships you get from this equation. So we're going to use perturbation theory to calculate our k-dependent energies for each band n. So En of k and our new block functions, the u functions, un k, in terms of what they were at k equals 0, which are your sort of the known quantities that you start with. So this is, when we were solving our 8x8 Hamiltonian and tight binding, we were also calculating the periodic part of the block function. The part gets repeated, and those are the coefficients, right, that you calculate from that 8x8 matrix in the tight binding approach. And then to get the full wave function, you multiply those coefficients by that block sum basis, which has that e to the I k dot r built into it. And so it's sort of the same thing here. Okay, so let's look at the first order correction to the energy. So first order, okay, so the perturbing terms, what we start with the this equation at k equals 0. So at k equals 0, right, these terms are not there. These two terms are 0 at k equals 0, right, because they have a k in them. Right, those two terms are not there at k equal to 0. So at k equal to 0, this just looks like your Schrodinger equation. Your normal old Schrodinger equation. P squared over 2m plus v acting on u equals e times u. It's your starting point. And then we're going to treat these terms. So these are the terms you treat with your perturbation theory. To ask how do things change as k starts to become non-zero, right? Because it's, for small k, those are small perturbations. And so you can use perturbation theory. The first order correction to En0 is En(k) is equal to En0 plus h bar over m k dot matrix element. The only operator in there is p. K is just a number, right? K is k. It's not an operator. The operator is p, the momentum operator, which is your grad. So you got to take this momentum matrix element N0 P N0. So, and well, what about this term? That has a K in it, but that's second order in K, and we're doing first order perturbation theory. So you only include terms which are first order in the thing you're perturbing with. That's why. For first order perturbation theory, that term is not there. The only first order term in K is that K dot P term, right? It's the only term first order in K. So do you all remember first order perturbation theory? That's, I mean, the change in energy, delta E, in case you've already forgotten Korotkov's course. Right? Delta E is, in this case, it's a change in energy, E Nk minus E N0, right? That's our delta E. And that's just the matrix element of your wave function with whatever your perturbation is. So N0 and whatever your perturbation is, usually in perturbation theory they'll call it like H prime, some perturbing part of your Hamiltonian. Does that look familiar? Okay, that's what we're doing, right? And our H prime is this K dot P term, right? That's all we're doing. First order perturbation theory. And I guess that's about all that we have time to do too. Yeah, well, we'll pick it up here on Wednesday with a discussion section Friday.